All right, we're going to be looking at some wave behaviors and focusing on mechanical waves in particular. We want to talk about resonance first, and that's just a sympathetic vibration. That means that the vibration of something at its natural frequency that's caused by a vibrating source at the same frequency causes this resonance. That's what it is. So this is best understood with some examples. If you push someone on a swing, you have to push at the same frequency. So you have to push at the same time as it comes back to your hand. So as they come back to your hand. So that is an example of resonance. And then the next example is when you have a car that's next to you, perhaps you are that car, and whoever it is, has their music up so loud and the bass so loud that it shakes your car. So we can see this in this video here. So her hair is vibrating at the same frequency as the music. So that's what's making it stand on end. And we have a few more examples. If you have water molecules that are being vibrated by a microwave oven, then they also are vibrating at the fundamental or natural frequency, and that is an example of resonance. Or when you have to rock your car to get it out of the snow, you have to push just as it's pushing, as it's coming back, in order to build up momentum and to have resonance with it so that you can get it out of the snow. And then there are a few other examples as well. And in fact, if you want to get pull waves large enough to splash out, you, rather than doing a cannonball, you can work the waves back and forth until they get bigger and bigger. And that will lead us to reflection and then also constructive and destructive interference, which I'll talk about in just a second. But first, let's start with wave reflection. This is just when a wave hits a barrier, like when you drop a rock into a puddle, and it develops these ripples until it hits a barrier, and then it hits the barrier and it comes back and it's reflected. But it's not reflected exactly the same way. My picture's poor as usual, but you can see that it bounces back, but it has an inverted or upside down amplitude. So then we have interference, and that's when waves get put on top of each other when they're at the same place at the same time. So they interfere with each other when this happens. And there's constructive and destructive interference, and that's when their amplitudes add. You can either have positive addition or negative addition, and that would be subtraction. So for example, if they're both in the same direction, so for example, here we have 5 centimeters positive and 10 centimeters positive, so both are positive amplitudes. They're heading toward each other, and the 10 and the 5 add to 15 so that it gets taller. You can also see this when you have waves in a pond or ocean, and they come together, and then they start off somewhat small, and then they get big and go boom and crash and are much taller than they started off. Destructive interference is just the opposite. When waves are out of phase, they have a positive and a negative, or a negative and a positive. For example, here we have a positive amplitude going to the right and a negative amplitude going to the left. When they come together, they cross out and go away. This is seen and used for noise canceling headphones. And then here we have a few questions. Where do you think the greatest constructive interference will be? Constructive is when they come together. So it would be the negative and negative here at D. That would get you the largest amplitude when they add together. And so that's choice D. And where will you get the greatest destructive interference? That would be B, because they are right on top of each other. Even if they're not the same amplitude, they're pretty close, and it would be the greatest destructive interference. So this one, it says, what will the resultant wave look like when the two waves are at the same place at the same time? And this is just the positive 3 added to the negative 5 centimeters. So then that gives you 3 minus 5, which is a negative 2. So then you can draw it just like that, and it's 2 centimeters down. So that's what the resultant wave would look like. Then we also have beats. This is interference between two waves that have different frequencies. It's at times that the waves have, it's when two waves have both constructive and destructive interference kind of at the same time. So you have alternating loud and quiet. Slow beats mean that the waves are close in frequency, and fast beats mean that the two are far apart in frequency. This comes into play for those of you in band. That's how you tune instruments to each other. You play them to a known note, and you make it so that you get rid of all the beats, or at least as far as you can hear beats. And then you add in instruments, and when the whole band plays together, you'll really hear the loud and then the quiet, loud and 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 quiet. And those beats will slow down and hopefully disappear once you get everyone in tune with each other. So this is a visual of that loud, where it's constructive, and then quiet, and loud, quiet, and loud, and quiet. And that's how the beats would be. So then we have standing waves, which is any pattern of wave crests or troughs that remain stationary in a medium. So you have to have, usually you have one or two waves going at the same time, and they're just offset in frequency so that they create this standing wave. So it looks like it's just one wave going, and they have a little bit of information that you need to know about them, some kind of vocabulary. And what we want to talk about are nodes, where it's where there isn't anything, and then antinodes, which is the high point or low point of that standing wave. Lambda is, again, wavelength. And in this case, lambda is equal to the length of the string. That's what L is. It's the length of the string. So the fundamental frequency is the lowest frequency, and L, again, is the length of the string, and the fundamental frequency is 1/2 of the wavelength. So this is only 1/2 of a wavelength. Remember, a wavelength would look more like that for a whole one, but this is just that half point right here. Okay, or the reverse, depending on how you want to look at it. No, look at the top or the bottom. So standing waves only come in certain types of, they only come in 1/2 wavelength intervals. So they have 1/2 lambda, 2/2 lambda, which is equal to 1 lambda, 3/2 lambda, 4/2. So you can see the number of nodes increases when you change the 1/2, 2/2, 3/2, etc. So this right here would be 3/2 lambda, and the 3 tells you how many nodes there are. So there's there's 1, 2, 3 nodes also, and then 4 antinodes in this picture. So then here's a picture of a standing node of some polystyrene beads, and it's just a box of, like, a tube of polystyrene beads, set to a certain frequency. Okay, well, I didn't mean to hit a stop, so I'm just going to restart the video. And here is an example of levitating beads caused by standing waves. So they created standing waves, and then they are making it so that it is picking up the beads. The beads are following the waves, and then they are changing the focus of those waves so that they can actually move. Though usually waves don't make things move. And you should recognize this. This is a resistor. So this is an ultrasonic focal point. So then the standing waves make it so that they can suspend things in air and you can see them because of the dry ice. That's dry ice right there. These are particles that are trapped in the nodes of the standing waves. And because they're trapped, you can move them if you change the focus of the standing waves. So you can do cool things like this. So here you can actually see the standing waves. Then they because they moved things around, now they can move the beads because they're moving the waves. They're moving the waves in 3 dimensions, not just 2. That's a diode and then a resistor. Well, actually a resistor and then a diode. I can't tell what that is. A wood piece. Looks like a matchstick. A screw. A nut. Plastic parts. Droplets. Looks like they're water droplets. The workspace is still, you can still touch it with your hands. That's just what that showed. Okay. Anyway, then we can talk about the fundamental frequency is the lowest frequency that an instrument can play, and it will be determined by the longest standing wave that will fit from node to node within the instrument. So the fundamental frequency is the length of the tube equal to 1/2. The length of the tube is equal to 1/2 of lambda. The second harmonic is equal to the length of the wavelength. The length is equal to the wavelength. Remember, it's 2 over 2 lambda. The third harmonic is 3 divided by 2 lambda. So there are 3 nodes in that length of tube. And then the fourth harmonic is 4 over 2 lambda. So it is 4 divided by 2 is 2. So it's 2 times the wavelength. So in order to change the frequency of the wave made by a wind instrument like a flute, the wavelength of the fundamental frequency is shortened by making openings in the tube. So you're lifting your fingers up off the flute. Then with a stringed instrument, higher frequencies are made by shortening the string by clamping a finger close to where the string is played. So that's why you are moving your fingers on the frets of the guitar. So the next behavior is called the Doppler effect, and this is when it sounds like there's a frequency change because of how fast something is going between the observer observing the sound and the source. So this is like when a fire truck, you're standing still and the fire truck passes you, it sounds like the frequency changes as it passes you. So as it approaches, the frequency is higher, and there's a shorter wavelength. And as it goes away, the frequency is lower, and there's a longer wavelength. The faster it's going, the more shifting there is. When the sound is made by a stationary object and you're moving, you hear a certain frequency. If you could see it, it would look something like this. This is wave fronts where the lines are wave fronts and the spaces are troughs. The waves get compressed, the smaller wavelength and a higher frequency. If you are in this area here, you'll hear the sound slide from high to low, and then waves get stretched. A big lambda is a lower frequency. A bigger lambda is a lower frequency over here on this side. When the object moves at the speed of sound, the waves overlap and you get a sonic boom. So if you fly faster than sound and you're gone before the boom is heard. So as you travel faster, the bell wake front gets narrower, and there's a visualization here. So this is how sonic boom looks.
We're all used to the idea that light travels faster than sound. Think about thunderstorms. You always see the lightning before you hear the thunder, despite the fact that they both occur at the same time. Sound travels at approximately 330 meters per second, which is pretty fast. However, man has been able to beat this speed and break the sound barrier with supersonic travel. The incredible thing about breaking the sound barrier is that it not only produces an audible effect, but also a visible one. Take a look at this picture. You can actually see the effect on the air as the plane blasts through the sound barrier. Isn't that amazing? The reason why this occurs is because as the plane travels through the air, it pushes the air out of the way, which creates pressure waves that travel at the speed of sound. This is similar to the waves created by the bow and stern of a boat as it moves through the water. As the plane approaches the sound barrier, the air cannot get out of the way quick enough, and it is squashed together into one big shock wave that is traveling at the speed of sound. This shock wave begins at the nose of the plane and ends at the tail in steady flight. It forms a kind of cone shape that surrounds the plane, as can be seen here. The pressure inside the cone is not that much greater than normal air pressure. However, since this overpressure is released very quickly, it is audible as a sonic boom. Have a listen to one. There are actually two booms that are produced, one at the nose and one at the tail, which you can see in this video. However, they usually pass over observers almost at the same time, and so most people will only hear one. It's not just fighter jets that can produce a sonic boom. Perhaps the most famous form of transport that could break the sound barrier was Concorde, which was a commercial airliner before it was put out of use in 2003. Space shuttles can also break the sound barrier, but only when they re-enter the Earth's atmosphere. Well, that's all we have time for, except for this last fact. Humans are actually able to produce a sonic boom using their hands. The crack of a bullwhip is actually a sonic boom. This is because the end of it is travelling faster than the speed of sound. Now that's fun.
Okay, so that's what a sonic boom looks like. And then these are just various sonic booms that have occurred. A compilation of them. This is not working. Okay.